So in this last section of today, we will talk about we will introduce more about the panel data set, this format, and also the fixed effects estimate method to deal with particular panel data. Okay, remember at the beginning of section 2, we talk about the different diff estimation can be extended in the time dimension to include a multiple time period, and also it can extend to in the cross-section dimension to include multiple treatment group. Like in the case of the legal drinking age, that's extend in both the year and state dimension. So data with multiple periods for multiple units, may these units be a state in our example, or it can be, in other cases, it can be district, and also individual data. If we have panel data, for example, if we have a panel survey, we kind of check the individual's household for several years. For each year, we survey this household, the same household, and ask maybe their income, ask their consumption, ask any aspect of their life that they're willing to answer. Then for this data, because we survey multiple households for multiple periods, so it will also be a panel data. Firm, we can have more example, like if we extract all the listed firms' annual report from some database in the library. So for each firm listed in the stock market, we will have their the number. We will have their balance sheet, their cash flow sheet, and any financial or their performance data for any year. So we actually have multiple firm over multiple years in this data set. So it's also a panel data. Panel data is actually a very common forms of data that we will deal with. It actually offers us new opportunities, at least to the definitive case. We can expand the most simple forms of definitive to accommodate more complicated policy changes setting or test setting. But they also pose more challenge for so that we can use that for education, but they also pose challenge to deal with that. So in our, normally, in practice, handling panel data is more tricky than the standard cross-sectional data we have dealt with so far. So the observation in panel data have two dimensions. Let's go away again, both the cross-sectional dimension, so in the minimum legal drinking age example, that would be stay, and also at the time dimension. So in that example, that would be year. In total, we have 51 stay over 14 years. So we have 714 observations in total for that example. And normally we will write the equation, the dependent variable in that cases, the mortality rate, y, we will have this subscript st. It actually indicates variable y is from the state s in the year t. It contains two dimensions. The subscript will directly point to the dimension of the data. So we can actually arrange, in R, we can actually arrange the panel data in two different ways. You can either arrange in long format or a Y format. So the Y format will be one observation is referring to 1 year. And for each of the variable, the columns will reflect, we will have the variable for one particular state as one column or variable. So this is an example of wide format. So for year 1, we have the state 1 mortality rate here, state 2 mortality rate here, up to state 51, right? And then we have maybe the legal drinking age proportion is for the first stage, for the second stage, and then up to the 51 stage in our example. And in total, we have a year like 40 years. This is a Y format. So the Y format typically will be the unit, each of the row will reflect on at the row side. It will contain only one dimension. Okay, one dimension. That will be the Y data. Well, actually, you can transpose this data set. You can have like one stay as a row, as observation as well. For example, so each of the observation will be 1 stay, 2 stay, 3 stay, up to 51 stay. And then you will have the Y in year 1, Y in year 2, and Y in year 14, the same for X variable. This will also be a Y format for the panel data, this panel data. The only difference is now at the row, we will have 51 stay instead of 40 years, okay? On contrast, the long format, we can also call it the stack format. One observation is for each stay in year. So in the row, it will contain both of the 2 dimension. So in R, you can use the command mel and cast to change the Y to long, using the mel to change the Y format to long format, and using the cast function to change the long format to Y format. You can change between. And remember, the mel and cast function actually come with the reshape library, but you can also use the tidyverse. Remember, in tidyverse we have the arrange functions in the prior. We also have some functions can allow us to change the Y format into long and the vice versa. Okay. So either one, they will do the same. So you can choose either function that you want to deal with. So the long format, this is an example of the long format. So for each observation will be 1 stay at 1 year, and then the mortality rate and also the legal drinking proportion of youngster. First stay, 2nd year, and then the 2nd stay, 3rd year, the 2nd stay, the 2nd year, and then go vice versa. So we have 2 dimensions in the row. This is the long format. So again, in R, we can use the mel function in the come with the reshape library. Remember, you have to install the library reshape using the install package function to install that. For the first time, we use this library. And then each time you open R, you have to load in using this library reshape command. And then using mel, you can actually change your Y format data into a long format. Now here, suppose, in fact, this is a more complicated example. In fact, so each of the ID plus the time will refer to 1 dimension in this example. And then x1, x2 is referring to, for this x at the first and second observation, that will be the 2nd dimension. We want to actually merge into the long format. So in the command, exactly. So in the mel command, first we put inside the data. We put inside the my data. And we have to, at the 2nd argument in mel function, we have to tell R exactly the identifier for our the dimension at the row. Because now at the row, each of the row is actually defined by both the ID and time. Right? Combine these 2 variables, we have the unique observation. So we can tell the ID, this ID is referring the ID in this command. That will be the ID unique identifier for each row. that will be indicated by the combination of the ID and time variable in the data, right? So we put it into a vector, and then put this vector into this ID argument. ID equals to this vector. So the unique identifier, we're actually telling R the unique identifier in this wide, for each row in this wide format of data is actually contained in this vector, okay? And then we map this data to generate a new data called M data. So you can see this is a new data, this command generate, that will be the same for the ID and time is the same as before. We have a 4 combination, but now we also have the variable. We will also have x1 and x2 here. So now it's in the long format, and this value we're referring to this trunk will just be this one, and this trunk will just be this one. Okay, so this is how we actually reshape the data from wide to long in R. So to think about that, to run a DD regression, what kind of data do we need? Do we need a long data or wide data? Think about that. So in the example, for example, in the example of minimum legal drinking age, so we will have the y st equals to alpha plus delta, right? Legal. That's also st, and then plus the sum of beta k stay s, and the sum of gamma et, right? Gamma j and plus ei, right? So look at this equation. To run this equation, we have to have the data. We have how many data we actually add? We have the moral drinking age. We have the legal, and all this data is in the ST. So each of the observation will be the legal drinking age for 1 stay and 1 year, the mortality rate for 1 stay and 1 year, and then I generate a bunch of this dummy variable, right? So in what formats data should we actually need? Again, this for that equation, we need a mortality rate for 1 to 1 stay year, 1 year, 2 year, 3 year, up to 40 year. And then the second year stay, oh, sorry, I should write it this way. The stay year, mortality rate, and then legal. 1, 2, 3, up to 14. And the second stay, 1, 2, 3, up to 14, and etc. So this should be the data I have, right? Each of the observation will be for 1 stay and 1 year, so exactly long format that we need. And again, okay, this is how we write this equation. The regression for this extend flexible definitive, we ran the moral the mortality rate on this legal drinking age proportion, and also have this dummy. Because we included the dummy of the stay and the dummy of the year, and I already tell you in the last section, this dummy of stay is actually controlling the average mortality rate for each of the stay over a different year. And this year dummy will control for the average mortality rate for each of the year over different stay, right? So we call this, because by doing this regression, we control the average. Actually, we control for average. This dummy will both saw the average legal drinking age and also the average mortality rate and also the average legal drinking age. So we call this model with stay and time fixed effect. So we call this dummy which contains the fixed effect. Okay, this stay fixed effect and also time fixed effect or year fixed effect. Because by including a dummy for every stay, but exclude one, we are holding the stay's effects, meaning the mean constant, the same for the year effect. That is why we call it a fixed effect. And because the data is in 2 dimensions, and we also add 2 dimensions of fixed effect, so sometimes we also call this model the 2-way fixed effect model. Effects. So we have estimated regression by actually folding in a dummy for every stay for 50 dummy variable. Say the R. Formerly, we normally use state as the software, but now it should be R. Can handle regression with more than 65 regressor. So R can handle even more. But what if we have more units like individuals or firm? Like this is stay and year levels, right? But how about if I have maybe in China we have nearly 3,000 listed firm. Maybe we look at the annual report for maybe 5 years for this 3,000 firm. So if I run a regression on that, I run a 2-way fixed effect models on that, I will have over 5 years, right? So I will have 5 dummy, and I will have all the unique dummies for each of the firm, right? So there will be a bunch of, if you look at the result, there will be a bunch of dummy variable in my regression. But think about that. So that doesn't seem very clean or parsimony. It doesn't seem very elegant, right? Can we do it in an more elegant way? Remember, each of these dummy variable, what we are trying to do to adding this dummy is trying to hold the mean of stay or the mean of the year constant. So this dummy variable, as we said, it actually contains the mean of the dependent variable and the regressor it actually contained in this fixed effect. To think about that, what am I mean? So we start with regression without time effects. We only add the 1 dimension of the fixed effect that will stay. And if we take the average across a period for each of the stay, and then we add that we replace this stay by year observation with the mean of stay. This will be what we have, right? The mean of mortality rate by over different stay, and then over different year for each stay. And then the regressor will be the legal proportion of legally drinking youngster at different stay over over each year, over all the 40 years. Notice that now the stay dummy does not vary over time, so it doesn't change by averaging. Now subtract this from the original regression. Like we have two regressions, right? And we can subtract them together. Subtract the right-hand side and the left-hand side, we will have exactly the same thing. So this mortality rate by stay and by year minus the average mortality rate for over different period for each of stay is equal to alpha, so minus alpha, and then plus this one will be this one will be just the same for the regressor. So at stay year level minus the for each of the stay, the average over a different year. Again, for this part, because this dummy, for each of the stay observation, you have one dummy, right? But these two parts are exactly the same. So in fact, essentially, you can consider this part as just zero, just canceling out. Because for each of the stay, it will be the same dummy variable. So this part cancel out, and then the error term is here as before. So you can write it as just, because alpha and alpha also cancel out. So this, the y variable minus the mean is actually equal to delta times the x variable at stay year level minus the mean at the stay level. The same for the error term. We call this, we call this process the demeaning process. So for both the dependent variable regressor and the residual, we subtract the mean by one dimension from that. It will be the same as this equation will still hold. And we can have a different way to solve that. So the dummy variable regression, again, only have the stay dummy. And the different from mean regression, this is something we derived just now, right? It actually both two regression, either this one and this one, actually produce the same estimate of delta. So this is, the delta will be the same, right? We set it. So in this process, the delta, we only have one delta. It's the same estimate. It will not change by either using the dummy regression or using the mean method. The deviation from means regression does not estimate, but instead, this demean function does not estimate alpha and the beta k betas. So using a demean function, because what we really care is still delta, right? The alpha and a bunch of beta is just a byproduct of that. And it is said if our data set that the time dimension cause section dimension, if they expand, we can have a lot of beta in our regression, both first of all, the computer will need to produce a very long list of this alpha and beta estimate for us, for which we don't need. What we still care about is only the delta. So instead of using the dummy variable to demean, to hold the mean effects constant, we can use this deviation from means regression or demeaning regression to estimate delta. So doing deviation from mean, we also call this regression the absorbing, it actually absorbing the fixed effects, or it actually, we also call it a within groups estimate, because we control for the mean difference, so it's only, we control for the between group mean difference, so we only relies on the within group variation. So exactly doing that in R. If before we're talking about the mean regression, we still go back to the two-way fixed effect with dummy, using dummy regression. So how to run dummy regression? Before we actually define the factor variable stay and factor variable years, and then put it into the regression. But instead, we can actually just put this. We can actually combine this. Save one step. We just put factor function. We'll put the state variable into this factor function and then directly put it in the regression. It will be the same. And the same for the factor variable of year. Basically, it would do the same as before, just telling okay, treat these two categorical variables as factor for me. Treat it as factor, meaning that generate all the dummy variable for me and put it in the regression. And then remember, if you have all the dummy for stay and have all the dummy for year, you can't absorb all the degrees of freedom. So you have to exclude the alpha. So at the -1, exclude the alpha. Well, actually you can, in practice, if you don't write this -1, it will directly, it will automatically kind of flow one factor, either stay or year away. We will omit that from the regression estimate. So that would be the same. Either way, you have to have at least 1 degree of freedom. So for the regression. And again, but all this, the beta, we don't care about. Okay, what we care about is still the delta, the estimate of this legal variable. Okay, the effect is 10.5, so it's very significant with the t-value 19.05, very significant at the point, maybe at 0.1% level. This is how we do this dummy regression in R, two-way fixed effect in R. But in the case that we want to exclude the stays effect, then we will put this, we will exclude this factor year part in the equation, only at the factors of year. And what's the result? Now we can also have a significant result for the legal drinking age. But now, if you don't control for the holding the mean of stay constant, you can see the estimate effect is actually negative and it's significant. obviously it's a bias estimate because we didn't take into consideration the group difference, the mortality rate difference between different stay before the treatment. So now we have this bias estimate of the causal effects. The same for if we also rule out the year fixed effect. We didn't hold the year fixed effect constant. Again, we have a negative estimate of this legal variable. And it's also significant, meaning that, okay, now if based on this result, we conclude that kind of lowering the legal drinking age included those youngsters under age 21s, include a larger proportion of them to be able to drink. It actually reduced the mortality rate. So think about that. For this particular t-test, what kinds of type 1 or type 2 error we are actually making? Because now we know this is not a true estimate, right? So this is not a true coefficient. This is actually a bias coefficient. So its meanings that this is the false num hypothesis, but we kind of reject it. So we're also making the type 2 error, but more importantly, we actually have the omitted variable bias for this estimate. So exactly how can the fixed effect change the slope? Think about that. And we can use this graph to show you visually. So when we're running, so suppose this is the point, so the x will be the proportion of legal drinking age youngster, and y is the mortality rate. Okay, and this is all the data so we have for each of the stay over different year. And for this point, we fit a regression line without controlling the fixed effect. We just run a very simple regression like this one. Okay, run the y as t equals alpha times delta legal as t, and then the e as t. So no fixed effect. So what kinds of outcome we will have? This is what we will have, right? We will have a straight lines like this. It's this black line. It's the regression line that we have. Now we can see the delta is actually smaller than 0. This is the pool. We also call this the pool regression line. Pool meaning that we pool all those data at different dimensions together and didn't control for the fixed effects. What about if we control for the fixed effects? If we control for the fixed effects, if we add the fixed effects in this model, the fixed effect of stay and also fixed effect of year, then it's like this one. So for each of the stay, so for the blue line, it's, for example, the data for each of the stay. And we separately estimate the, we separately run estimate the regression line. And the second pool, and the second bunch of data for the second stage, the red line, we run another regression. And the third one, we run another regression. This is the result we have. Now we will have a positive delta for each of the state. So your turn. This is the question for you. In the graph I just showed you, the confounding variation is related to A, the different state. In the graph, that would be the blue, red, and black group, or different time period. Variation within the blue, red, and black group. So here, the confounding variation. Now, this is after we use a fixed effect to solve the confounding. That will be for each of the group data point. For example, here instead of 51 states, we only have 3 states, right? The blue one, the red one, and the black one. So each of the point will be represented for that particular state, the data at different year. So we run the regression again. Here we have the delta. So the question actually asks, by running this regression with fixed effect, the confounding variation, if you compare this first pool regression line and the fixed effect regression line, the confounding factor is actually coming from the state of the year. 5 seconds. Yes, the answer is A. So now you can see, look at this graph. We actually we actually holding the state constants, right? We compare within the state. So for the blue state, we compare and draw a line. We compare the data over different year. For the red state, the same. For the black state, the same. This is how we got the fixed effect regression line. So the confounding factor, by comparing these two graphs, comparing the pool and the fixed effect regression line, the confounding variation is actually related to different state. So again, remember at the beginning, at the definitive estimate part, we talk about definitive require each of the state will have each of the unit, or you should say, will have this parallel trend over time. If we, without the effects coming from the treatment, they should have the parallel trend. So let's see if that makes sense. Remember how we assess the parallel trend for the data. So we will look at the outcome variable for each of the group, both treatments and control. In this particular case, because we have multiple treatments, so we will compare for each of the state. So we compare in the period that outside without treatment. We want to see whether relatively for the outcome variable, they have parallel trend. Okay. And this is the result that we have. It looks more or less parallel, but right, it looks more or less parallels, which give us some confidence to use a definitive model. But let's look at it deeper. Consider there is consider standard DD. there will be the death rate for only Tuesday. We compare the a Kansas, remember, that's the control group without any change of the legal drinking age, and the Alabama, one's lower, and then, one's lower the legal drinking age. Oh, sorry. No, that's a different example. Sorry. So in this example, the Alabama actually didn't change legal drinking age, and for another state, what's the state? Alexis is a state actually changed the legal drinking age at 1975. So the parallel time trends mean before the treatment in 1975, between the year of 1970 to 1974, the death rate is growth at the same rate for both states. And then after treatment, it also grows at the same rate. But the difference, counterfactually, if without, for this red line, if without the treatment, the counterfactual outcome will be like this, right? So the difference between the counterfactual outcome and the actual outcome after the treatment, this will be referring to the treatment effects. In the case that if this Tuesday, both the control group in the blue line and the treatment group in the red line, if they have a different time trend, then think about that. After the treatment, if again we apply treatments to the second cases, maybe to the maybe here we can draw it. It's the same at 1934. We apply a treatment which increased the death rate of the state. And then after this change of level, this state will kind of follow the same trend as before to growth. Now, because we always use if we still use the time trend of the control group to control for the trend effects, we use the control groups as the counterfactual, then we will have, maybe I should change the color. Then we draw a parallel graph here. Oh, sorry. Because the treatment is at this particular point, I draw it here. Right. So this is a parallel line. Okay. And then at the sorry. I should draw a pre-treatment. This line should go at the points when the treatment apply. It will be here, right? And then we still use the effects of the control group to derive the counterfactual. Can I directly draw a straight line? Why I no longer control? Give me some time. Oh yeah, this is better. And draw a straight line. Okay, let's clean it all. And let me draw it again. Using a straight line. Suppose this is when the treatment apply, and then after that, and then after that, it will use the original growth rate, and then at the same time point, we will have, but we still use the control groups to estimate to rule out the effects of the time trend. We can do so. We draw a parallel line here. Okay. So this part will be the definitive estimate. Now you can see, because the pre-treatment time trend between the treatment group and the control group is different. Now, because this is the estimate treatment effects, but the actual treatment effects is actually here. Oops. Okay, so here. This is the true treatment effects. So we kind of overestimate, using this estimate treatment effects, we kind of overestimate the true treatment effects, right? Effects in this line. Why is that? Because the estimate treatment effect now is also contain the effects coming from this part. Coming from the trend difference between the treatment and control group. It happened to be this part is positive in these particular cases. So we tend to overestimate the true treatment effects. If in the case that the treatment group actually have a lower growth rate than the control group, then we are likely to be underestimate the treatment effect, because we will kind of subtract the trend difference from the true treatment effects in that cases. Okay. But with with this fixed effects and panel data setting, we can kind of relax the parallel trend assumption. Because with many periods, we can, by adding a new control variable to control for the trend difference, that is, we control for the state-specific time trend. Okay, how can we construct this state-specific time trend? That's actually, we have a theta, so theta k, because we have k state, right? So for each of the state, for the dummy variable, we actually times a time trend. Okay, so for example, for the state of Alabama, we have year 1970 to 1983 time trend, maybe like this. And then for the second state, we control another linear time trend. And the first day, third and fourth. So for this variable here, this variables here, is actually for each of the state, we control a linear time trend for that. That is like in this graph, we actually control that particular variable, actually control this delta A, LA, and also this, no, not delta, sorry, theta, right? Theta, oops. Yeah. The theta ALA, and also the theta ALL, theta. So this will be controlled by this new bunch of variable, but times the state dummy variable times a year, a linear year variable. So by doing so, because we already control for the different time trend for each of the state, we no longer have to worry about whether whether each of the state actually have different trend in terms of mortality rate among the youngster over time. Again, question to you. Can we introduce a variable xx, which is constant within state for this two-way fixed effect model? Yes or no? 5 seconds. 1, 2, 3, 4, 5. Right, the answer is no, we cannot, because if we add an xx to that, this effect theta will be absorbed by the state dummy, right? Because for each of the state, this xx will be the same. So it will be the same for the dummy variable. It will be absorbed by the dummy variable. So, right, this is the case that how we can use the state-specific time trend. After you add the state-specific time trend, it's kind of like for each of the state, you first control for this trend variable. We already control for this trend variable. And after that, the delta, the estimate delta, it gives you will be just the difference between, you no longer relies on the control group's trends to estimate that. So for this new regression, this part will be the treatment effects that estimate by your delta. And it is the true treatment effects. So in R, how can we have that? The other part, the same as before in the LM commands. So Y variable, mortality rate, and then wave, reversal legal, and control for the factor, the dummy of state, and also the bunch of dummy of year. And then we add another part. That will be the dummy of state times year. So remember, we remind, so the factor state times year is not equals to factor state times factor year. okay, these two are not the same as each other, okay? If you use the factor stay times factor year, you cannot add this variable in the regression. It will solve all the degrees of freedom. But that's exactly how your data is measured at the stay and by year level. But you actually can control for factor stay times year. Because that's the specific time trend. This year, now we no longer define it as a bunch of dummy. It's just a linear variable. It can be 1970, 71, 72, and to 1980, up to 1983. Or it can be 1, 2, 3, 4. That will be the same, right? Just a linear variable. And then -1 to exclude the constant. Now let's look at the effects. So after control the specific time trend, we estimate the legal. It has this is the delta, and now it's actually significant positive, meaning that although the number is much smaller than before after we control the trend difference, but now we know we actually get an unbiased, correct, true estimate. Indeed, lowering the legal drinking age in these kind of lead to more death among the youngster, significantly more. So now that's about the estimate of delta. Now think about the standard error for the panel regression. Our standard error calculation assume a random sampling, right? As a result of the residuals for any two observations should not be systematically related, okay? But the panel data actually have a time series dimension, meaning that, think about that, many economic variables are correlated over time, right? Think about that. The death rate, for example, the death rate for one particular stay at one particular year maybe have this correlation with the death rate at the past year, right? Because for those who stay have a very low death rate, it's very likely over time it will have the death rate is always at a very low stage. And vice versa, for a stay with a very high death rate at 1 year, and over the whole periods that we observe, the death rate might be high. So, meaning that the regressor, it's the residuals for this panel regression actually can have to have some series correlation over different time period. But in these cases, we can apply a robust standard error. We introduced a robust standard error before to dealing with the heteroscedasticities problems, right? And that can allow for a non-parametric correlation between residual and regressor. But the robust standard error can not solve the problem if the residual actually correlated with each other over time. So we cannot use a robust standard error to solve this correlation, this time series correlation in the panel data set. So we introduce another way to adjust the standard error. That's called the cluster standard error. The cluster standard error allows a similar correlation between residual from different periods within each stay. So each stay will be one cluster. And normally for cluster standard error to work, we will need enough cluster for And normally by enough, it normally will be something around 20 or more than 20. It will be a satisfied number. So if you want to add a cluster to a standard error, you better have more cluster than 20, okay? So whenever we talk about, this is the foremost two-way fixed effect model. And we can also do the cluster. We use the LM.cluster function instead of the LM functions to estimate the regression. By this function, it allows us to add one argument, that is the cluster. So for this function, we tell our data is this depth data, and the formula is as before, just depth ray, wave, x key regressor, and the fixed effect of S day and fixed effect a year. And then the third argument, we add the cluster will be equals to, because we want to cluster. Remember what kinds of serial correlation of residual that we worry about now, that is within each of the stay over different time, the mortality rate may be correlated with each other. The same for the legal drinking age, right? So we should actually cluster for each of the stay, meaning that for each of the stay, now clusters the standard error for me, solving this series correlation for me. So we define the cluster using this stay variable. And this is the result we have. No matter whether you apply the robust standard error or cluster standard error, you only change the standard error, but it doesn't change your coefficient, the estimate of your coefficient. So again, as before, we have the estimate of this legal variable. It's still without cluster the standard error, there will be 10.5 significant, and now it's also 10.5. But you can see the standard error compared to before. The standard error is actually, the cluster standard error is actually getting larger compared to the conventional standard error. But still, even with this larger standard error, and thereby our t-value, because the estimate coefficient is no changes, but the standard error in the denominator get larger, so we will have smaller t-value, but still drop from 19.05 to 15.52. The t-value is still very significant, okay? But now, because with larger standard error, meaning that we're less likely to make the Taiwan error by using the cluster standard error. So remember we said you can have different type of reasons for that, right? For dying, right? We can actually using those dying rate by car accidents compared to dying rates by other internal causes like cancer as the robust check for our result. Because the policy shock to lowering the legal drinking age should only affects the death rate for the motorcycle accident, but not for suicides or the other internal causes, right? So this is how we do it. Now we also talk about how to weight the regression to get more reasonable estimate, but because we haven't introduced the weight, the concept of weight regression yet. We will introduce it in last class. I kind of reject the orders of class this week. So we will mention this weighted regressions in the next class. So let's only look at the first two columns because we don't care about whether we weight the regressions or not now. So for the two columns, the first one is without the control, the specific state-specific time trend. The second one will be control. So now we kind of change the organization of the tables a bit. So now the row will reflect the dependent variable. So each of the row will be one, each of the cell will be one regression, okay, result, right? So if we use all the death rate for all the cause of death as dependent variable, the delta, this is a delta when we have, so the t value will be around 2, right? Should be more than 2. So it is still significant. And if we only look at those death rate by motor vehicles accident, this is the result, coefficient and standard error. And the t statistic will be less than 3, more than 2, so it's also significant. How about if we're using the mortality rates by suicide? So this is a result, and then t statistic is 1, is not significant. So that is something that we expect, right? Because changing the legal drinking age should not hasten the death rate by suicide. The same for the internal cause, like cancer or other disease, is also not significant. Okay. How about the second column? If we control for the time trend, after we control the time trend for all the death, A divided by 5, it should be lower than, smaller than 1.96, so it's no longer significant. But the second one, by motorcycle vehicle accident, is still significant. That's what we want, what we expect. Suicide, continue no significant, or the internal cause, and no significant result. So this is consistent as what we expect. Give out more confidence that the legal drinking age indeed has causal effects on mortality rate specific to the motor vehicle accidents mortality rate. So let's summarize how this fixed effects actually eliminates bad variation. Unlike the regression, definitive and panel data fixed effects estimation rely directly on the linear educated regression models to eliminate the parallel trends across day or at the other units like time. So the linearities is not a convenience approximation anymore. Specifically, specification is therefore more critical. For example, if a trend are parallel in level, they can't be in log. Okay, now it's different as before. So the DDs and fixed effect models are an alternative strategies to eliminate bad variance in the original data and leave us with good variation. The key question now is, are the confounders only related to cross-sectional variation that we are capturing with the fixed effect? If that is the case, then the diff in diff in the fixed effects model would be a good strategy, right? But if it is not, we have to think about how to expand that a little bit. So this is the last question you should consider in your estimate, in your causal inference using the diff in diff in the panel data and fixed effects estimation. To sum up, the diff in diff and panel data fixed effects are methods to analyze policy changes. So panel data with many cross-section unit and time periods pull many such policy change together, and each single one of which might be too small to yield useful estimate. But if you put them together, more likely you will generate reliable estimated result and also reliable statistic tests for that. And the fixed effects can be introduced as a dummy variable for cross-sectional unit, like stay, and also a time unit using time period. The deviation from mean is an alternative way of estimating fixed effect regression. The fixed effects get absorbed in these cases when you use the demeaned regression, and they will not be estimated directly by the dummy variable. This let us deal with the panel which would have too many fixed effects to actually estimate. Sometimes when you have too many fixed effects, it may be hard to get estimate. The calculation will continue for the computer will continue for such a long time. In that case, actually doing this demeaned regression kind of save a lot of computation efforts, computations for that, for estimate. And also in a panel with a large time dimension, we can also relax the parallel trend assumption by adding the unit-specific trend. In the case of the legal drinking age example, there will be the state-specific time trend to kind of control for different trend, the trend difference across the unit. And using this as a specification check on your baseline specification. Okay, so normally, if we do a regression, we will not do this full regression at first, control for all the stay and year fixed effect, and along with the parallel trend. We will create this table. Maybe for the first column, we don't control for the time trend. For the second column, we do to control, and by comparing the estimate of the coefficient, we can tell whether the time trend actually kind of bias the estimate. And finally, because in the panel data setting, because most of the variable for the same unit, they have this time series correlation with each other, meaning that if you run the regression directly on this two-dimension data, in the residual, we may have the residual contains some part of the variance that is correlated with each other. In these cases, we need to cast our standard error. We cast the standard error by the cross-sectional unit. If you have enough cross-sectional unit, normally more than 20, it will be a wise strategy to do that. Normally, by casting your standard error, you will come to have a larger standard error. And by that, you will have a smaller t-value, meaning that you're less likely to making Taiwan errors in your statistic testing. Thank you, and see you next week. This is all for today. See you next week.